We are now going to discuss current. Current is charged particles in motion. These charged particles could be electrons in metals, electrons in holes in semiconductors, or ions in space. The unit for current is the ampere, and 1 amp is equal to 1 coulomb per second. In metals, the current is carried by conduction electrons. These are electrons that are free to move about inside the metal. Let's assume we have a block of metal. It could be like a piece of copper. And let's zoom in and take a look at one of these conduction electrons. So this dot will represent a conduction electron in a metal. What you would observe is the electron would be moving and then have an abrupt change of direction, a randomizing of the direction it's moving. This randomizing of the velocity of this electron is due to things that are called scattering events. The most significant scattering event is lattice scattering, and this is an interaction between the conduction electron and the vibrating lattice. As the temperature goes up, the amount of lattice scattering increases. Other things that can cause scattering are ionized impurities or defects in the crystal lattice. We are not going to discuss the physical mechanisms behind these scattering events. But let me just point out how ionized impurity scattering works. So here I'm picturing an ionized impurity in the lattice. So as a conduction electron goes by, there's a coulombic attraction to the ionized impurity, which is going to change the direction of the velocity of the electron. In between scattering events, the electron will travel some distance over some time. If you follow the electron for a while and sum up the total distance it has traveled and the total time, you get what is called the thermal velocity of the electron. At a temperature of 300 Kelvin, which is around room temperature, the thermal velocity for electrons in metals is on the order of 10 to the 5th meters per second. So those electrons are moving with a very high velocity. Often the conduction electrons in a metal are referred to as an electron gas. The behavior of the conduction electrons in the metal are just like the behavior of air molecules in a room. Let's now apply a voltage across our conductor. For the applied voltage, the electric field intensity will be to the left. The force on the conduction electrons is the charge on the conduction electrons times the electric field intensity. So that force will be pointing to the right because the electrons carry a negative charge. Again, let's zoom in on the electron and watch its behavior. The electron still has its thermal velocity, but now there's a force trying to accelerate it to the right. But then it encounters a scattering event that randomizes its velocity. So slowly the electron will drift to the right. If you take the distance the electron has moved over some time and divide them, you get what we call the drift velocity of the electron. The drift velocity is just charged particle motion in response to an electric field. We will make the calculation later, but this drift velocity is much, much, much less than the thermal velocity of the electron. If you could actually watch an individual electron, it would be almost impossible to discern that there's actually a net drift velocity. It would look just like a random thermal motion. So I really had to exaggerate in this figure to illustrate the concept of drift velocity. Even though we know that current flow in a metal is due to flow of negatively charged electrons, we treat current as a positive charge flowing in the opposite direction. This is a remnant of Ben Franklin's guess as to the direction of his electric fluid flow. Even though current flowing in a wire is due to negative charges, let's see that negative charges moving to the left can be treated as if there were positive charges of the same magnitude moving to the right. So in the top wire, I have 1 coulomb per second flowing to the right, and in the bottom wire, I have minus 1 coulomb per second flowing to the left. And we'll have a charged reservoir, which will be our ammeter for measuring the current flowing in our wires. At t equals 0, we're going to set the total charge to 0 in our two reservoirs. So we'll have an equal number of negative and positive charges in each reservoir. Let's first focus on the wire where there's a positive 1 coulomb per second flowing to the right. So after 1 second, we'll have 1 coulomb flowing into the reservoir, so now it will have a total charge of 1 coulomb. After 2 seconds, another coulomb of charge will flow into it. We'll now have 2 coulombs. After 3 seconds, we'll have another 1 coulomb flow into the reservoir, so we'll have 3 coulombs in the reservoir. Now let's focus on the wire with the minus 1 coulomb per second flowing to the left. So after 1 second, we'll have a minus 1 coulomb having flowed out of our reservoir. So the net charge in our reservoir will be plus 1 coulomb. After another second, another minus 1 coulomb will have flowed out of the reservoir. Now we'll have a total of 2 coulombs. After another second, we'll remove another minus 1 coulomb. So now we'll have a net of plus 3 coulombs. So what we're observing, the charge in our reservoir, is the same whether the flow is due to positive charges to the right or negative charges to the left. Even though we know current in metals is carried by conduction electrons, we see that we can treat the current flow as equivalent positive charges moving in the opposite direction. Let's look at how the factors of the electrons and their velocity determine the current that is flowing. So let's assume we have some conductor, such as this rectangular shaped object, and we apply a voltage, so there's an electric field to the right, and let's assume that the conduction charges are positive, and hence they will flow to the right. We'll put up a plane of observation, and we'll count how much charge flows across the plane and divide by the time. That's the definition of current. So in a time t, the conduction charges will have drifted a distance u times t. If the cross-sectional area of the conductor is A, then all of the charges, the conduction charges in the volume A times ut will have gone through our observation plane. So u times t times A is that volume. So a distance times a cross-sectional area, and the units are meter cubed. The symbol N will represent the number of conduction charges per unit volume. So N times the volume will just give us the number of charges, conduction charges, inside this volume. Q is going to represent the charge on each of these conduction charges. So multiplying the number of our conduction charges by the charge per conduction charge will give us the total amount of charge that flows through our observation plane. Now we divide this by the time that we've been observing the charge flowing through our plane, and we get the number of coulombs per second flowing through our plane, which is just our current. So we have our equation relating the charges and their motion to the current that's flowing. Now you should have a model of what's happening so that this equation makes sense. It's something you could just write down. The faster the charges are moving, the more of them will go through your observation plane per second. The greater the cross-sectional area of your plane, the more charge you'll have going through per second. The greater the density of the charge, the greater number of charges will go through your plane per second. And to get to a current, you know it's a charge flow per second, so you have to multiply by the charge of each of your conduction charges.